Bismillahirrahmanirrahim. Assalamu alaikum. This is Faryal Javed, rule number 21TE07 from Telecommunication Engineering Department, UT Texila. So today I am going to solve lab manual 10 of digital signal processing, that is frequency sampling design method. And the lab objective of today's lab is implementation of FIR filter using frequency sampling method. Basically, in frequency sampling method, FIR filters are designed by the desired frequency response, and this method involves sampling the desired frequency responses at equally spaced intervals and then computing the impulse response using inverse Fourier transform. And here, as you can see, the resulting impulse response is of finite length, making it suitable for FIR filter implementation. Moving towards task 1 of today's lab, that is design a linear phase low pass FIR filter with 25 coefficients using frequency sampling method. Let the cutoff frequency be 2000 Hz and assume sampling frequency of 8000 Hz. Plot the magnitude and the phase frequency responses. List FIR filter coefficients. Moving towards the output of our first task, and here, as you can see, here is the output to our task 1, the magnitude response and the phase response. So in this code we first calculate the cutoff frequency based on the given cutoff and the sampling frequencies, and then generate the impulse response of the FIR filter using frequency sampling methods. Next, it computes the transfer function of the filter by performing frequency Fourier transform on the impulse responses, and the amplitude and the phase responses of the filter are plotted to visualize its characteristic. So this code basically demonstrates how to design a low-pass FIR filter, visualizing its frequency responses, and to obtain the filter coefficient using frequency sampling method. And here is the 25 coefficients that are the transfer functions of this code. Moving towards task 2 of today's lab, that is design a linear phase bandpass FIR filter with 25 coefficients using frequency sampling method. Let the lower and the upper cutoff frequencies be 1000 and 3000 Hz respectively, and assume a sampling frequency of 8000 Hz. List the FIR filter coefficients and then plot the frequency responses. Moving towards the output to our task 2 of today's lab. In this code, we basically calculate the normalized cutoff frequencies based on given lower and upper cutoff frequencies and the sampling frequency. It then generates the impulse response of the band pass filter using the frequency sampling method. As you can see here, that after that we compute the transfer function of the filter by performing FFT on the impulse responses, and here is the magnitude and the phase responses of the filters. So in this code, we basically demonstrate how to design a bandpass FIR filter, and here is the 25 filter coefficients of the bandpass filter. Moving towards the third task of today's lab, that is find the magnitude response and phase for the following filters. Demonstrate the transfer function for a 3-tap FIR low-pass filter with a cutoff frequency of 150 Hz and a sampling rate of 1000 Hz using a frequency sampling method, and then determine the transfer function for a 3-tap FIR high pass filter. Then we have the FIR low pass filter, FIR high pass filter with a different cutoff frequencies, and then we have following specifications for a 7-tap FIR band pass filter with its cutoff upper and lower cutoff frequencies, and then they also give us a following specifications for a 7-tap FIR filters, and we need to determine its transfer function. So starting with the very first 3-tap FIR low pass filter with the cutoff frequency of 150 Hz and 1000 Hz. Yes, so here for each problem, we utilize a frequency sampling method to design a FIR filter and analyze their frequency responses. Firstly, we calculate the normalized cutoff frequency based on the specified cutoff frequencies, and then allows it to work within a standardized frequency range independent of the actual sampling rate. Once the impulse response is determined, we convert it to a frequency domain by performing a fast Fourier transform. This transform basically yields the transfer function of the filter, representing its frequency response characteristic. So, in the frequency sampling method, it is designed by basically by specifying the desired frequency responses directly. This method involves sampling the desired frequency response at equally spaced interval and then computing the impulses. By following these steps, we can design FIR filters and evaluate their performance in form of frequency domain characteristic. And here, as we analyze the magnitude response and the phase response of our first task, the same goes for the magnitude and the phase response for our second task. And in this code, we analyzes the magnitude and phase response for a transfer function to understand how a filter behave across different frequencies. The magnitude responses indicate the attenuation or amplification of input signals at various frequencies, while the phase responses represent the shift introduced by the filter across a frequency spectrum. Now the output to our task 3, the magnitude response for a 7.15 part and a phase response for a 7.15. Basically, once the impulse response is determined, we convert it to a frequency domain by performing the FFT. And basically, while the following the we generate an impulse response for a filter using a frequency sampling method. As I told you earlier, for a low pass and a high pass filter, we compute the impulse responses directly. While for a band pass and a band reject filters, we adjust the impulse responses to meet the desired frequency band specification. Here is the band reject filter. So for this band reject filter, we adjust the impulse responses to meet the desired frequency band specification. So this is it for today's lab. We'll see you in the next lab. Thank you so much. Allah Hafiz.